Okay, I'm back, and now we want to talk about what music is. So far, we've been adding basically two waves together. But just like ocean waves, sound waves are actually a combination of many, many different frequencies. So the loudness of sound is going to be related to the amplitude. So that if you've got a sound wave that looks like this, and then another sound wave that looks like this, then this one is going to be louder than this one. So the amplitude is going to be related to the loudness, and we have a special unit for the loudness of sound, and then that's going to be called decibels. And so for humans, we can barely hear the loudness of 0 decibels, and then 120 decibels is deafening for a human. So that's about the maximum loudness that we can withstand. Then you've got the pitch of a musical instrument is going to be related to its frequency. So the higher the frequency, the higher the pitch of a musical note. And so for humans, we have the ability to hear frequencies from about 20 hertz to 20,000 hertz. Now, quality is the most confusing. And so quality is the blending of the various standing waves produced by the musical instrument. So that what we've been doing is adding at most two waves together. But music consists of many, many different frequencies, and they're all blended together. So in this picture here, it's showing a green frequency being mixed with a blue frequency being mixed with a yellow frequency, and then it is producing the red frequency. So the red one is going to be the sum of those just three frequencies. Now imagine adding together 100 different frequencies. Well, that's the frequency of music. And so depending on the musical instrument, it's going to be producing different amounts of different frequencies. So this is the reason why on a violin you can play a C, but you can also strum a guitar at a C, and you could also play a trumpet at a C. But they all sound different. They're all playing the same overall frequency, but yet they have this individual kind of a sound to them, and that's because each one of them is producing different frequencies that when you all add them together you get a C, but they're different enough from each other that each musical instrument is going to sound distinctive in what it does. So when we blend all of these different frequencies together, we call that the quality of the sound being produced. All right, now how do we actually produce sounds? So there are three kinds of musical instruments. So you have stringed instruments, wind instruments, and then percussion instruments. So the easiest one to understand is the string. And so this is where you're going to have a string, and it's going to be connected to 2 points, and you could pluck it so that it made one standing wave in there. That's going to correspond to a certain wavelength, and it's also going to correspond to a certain frequency. But if you take your finger and you put your finger right here, well, now when you strum the guitar, it's now going to make a standing wave that's going to look like that. So it's going to have a smaller wavelength that goes with it, so it's going to sound different. So depending on where you put your fingers on the guitar, it's going to produce different wavelengths, which produce different frequencies. Okay, in the case of the wind instrument, all right, so in that we're going to have a tube, and the tube could be open on one end and it could be closed on the other end. And so that's going to produce different standing waves inside of the tube. But this time, depending on where you put your fingers, let's say that this is a clarinet, and then depending on where you put your fingers on the clarinet, that's going to produce different standing waves in the tube. Each one has a different wavelength, so each one is going to produce a different frequency. And it's the same thing even with a drum. So that there's some pictures of how a drum vibrates up and down. And so depending on where you hit the drum, you can produce different kinds of standing waves in the drum, which produces different frequencies of sound. So here's a sample question. A guitar string has a length of 0.75 meters. What frequency will it produce, assuming 3 standing waves? So your first step is to make a picture. And so here is 3 standing waves being set up, and then the total distance from one node to the last node is going to be 0.75 meters because it's closed on both ends. Okay, next we've got to remember that the distance from a node to a node is going to be equal to 1/2 of a wavelength. Well, the distance from the node to the node is 1/3 of the total distance all the way across. So 1/3 of 0.75 is 0.25. So 0.25 is equal to lambda divided by 2, which means that lambda is equal to 0.5 meters. All right, now finally, we need to find the frequency. So we're going to say that the speed of any wave is equal to its wavelength times its frequency. So the speed of sound in air is 340 meters per second. We're going to set that equal to the wavelength, which we just calculated, times the frequency, solve it for the frequency, and we get 680 hertz. Okay, here's another example. A jug is 0.5 meters tall. So you've seen like on the Beverly Hillbillies or something where they've got this jug of moonshine and they're blowing across the top of it and it's making a certain frequency. You know what I'm talking about? Go to Google Beverly Hillbillies. You'll see what I mean here. So what frequency of sound will the jug produce, assuming it has 1.5 standing waves in it? Now I took my jug and I tipped it over on its side. Okay, so that it's closed on one end and then the jug is open on the other end. Then I drew 1.5 standing waves in there. Okay, then I locate where my nodes are, which is where it's at its minimum. Don't need to worry about the antinodes. So the distance from a node to a node. All right, now the mathematics on this one's a little bit more difficult. It's going to be 2/3 of the way across is the distance from the node to the node. So 2/3 of 0.5, that's going to be equal to lambda divided by 2. So now we've got the wavelength, and now again use the speed of sound in order to calculate the frequency, and it turns out to be 919 hertz. Now, here's just something that I found interesting, that these are keys on a piano, and then these are the typical frequencies produced by piano keys when you tap them. Just thought that was interesting. I found that on the internet. Couldn't turn it down. Okay, let's take a break. When we come back, we're going to talk about the human ear.